Good afternoon, everybody. Now let us start. Adjoint of a linear operator. This adjoint of a linear operator. So we know already what is a linear operator. Okay. So now we'll see what is the definition of this adjoint of a linear operator. Let T be a linear operator. Let T be a linear operator on an inner product space V. Then we say that T has an adjoint. Then we say that T has an adjoint T star if T of x comma y inner product is equal to x comma T star y. Okay. So if T is a linear operator on V, that means T is mapping from V to V. So if there exists another operator and same from this V to V, and if this thing satisfies this property, like inner product of Tx comma y is equal to x comma T star y, then this T star is called the adjoint of T. Here T star is called the adjoint of T, called the adjoint of this linear operator T, and here this T star is the adjoint of this linear operator. So then come to next. So if A is any matrix, if A is any matrix, then what does mean by A star? And we know already A star means this is the conjugate transpose of A. This is the conjugate transpose of A. Conjugate transpose of this matrix A. That means suppose A is a matrix like this one, 2 plus I, 3 minus I, 1 minus I, this is plus I. So what does it mean by A star? A star means this is the conjugate transpose. That means first I will take conjugate, first I will take transpose, then conjugate, both are same. Suppose first I will take the conjugate, and then I will take the transpose. Then this is my matrix A. So what is its conjugate? For 2 plus I, this is 2 minus I. Then for 3 minus I, this is 3 plus I. Then for 1 minus I, it would be 1 plus I. Then for plus I, it is minus I. Okay. So this is the conjugate of A. Then what is its transpose? In transpose, I will change the rows into columns. So first row will be my first column. So this will be 2 minus I, 3 plus I. Then second row is my second column. So this will be 1 plus I minus I. So if A is any matrix, then A star is this one. A star means this is the conjugate transpose of matrix A. So why I told this one, because suppose T is a linear operator on V, that is T from V to V is a linear operator. If this is a linear operator on this vector space V, or T is a linear operator on an inner product space V, then what will be the matrix associated with T star? So if T from V to V is a linear operator, then the matrix associated with this, with the adjoint of linear, then the matrix associated with the adjoint of T, with the adjoint of T is given by, that is your T beta star, where beta is any orthonormal basis of V. And beta is any orthonormal basis for V. Beta is an orthonormal basis for V. So what we got? So the matrix associated with this T star, that is the linear operator of T, with respect to this basis beta, is nothing but this is the matrix associated. This is the matrix associated with this linear transformation T corresponding to this basis beta and its conjugate transpose. Okay, so T star beta is equal to T beta star. Now comes to another important thing. So let V be an inner product space. Let V be an inner product space. Let V be any inner product space. Let Y belongs to V. Let Y belongs to V. That is, Y is any vector from this vector space V. The function G from V to F. Okay, V is an inner product space. Y is a vector from V or any vector from V, and the a function is defined G from V to F. The function G from V to F is defined by G of x is equal to inner product of x comma y. Okay. So G is a function from V to F defined by G of x equal to inner product of x comma y. This thing is clearly a linear transformation, because we know already any inner product space is a linear transformation. So if I will define a function like this is as inner product of x comma y, G of x as inner product of x comma y. So this will be a linear transformation. So what is an interesting fact here? The interesting fact is the interesting the interesting fact is here that if V is a finite dimensional, if V is a finite dimensional inner product space, V is a finite dimensional inner product space, then every linear transformation from V into F is of this form. Then every linear transformation from V to F is of this form. That means if V is any inner product space and Y belongs to V, and this is a crucial point, how we are finding this Y. So if we got that Y, then any function g to f, if this is defined in this way, or if we define a function g from v to f is in this way, like g of x is the inner product of x comma y, where y belongs to v. This is clearly a linear transformation because this is an inner product space. So this will be a linear transformation. So the interesting fact is, if V is a finite dimensional inner product space, that means the basis of V is finite, then if you will see any linear transformation from V to F, this is in this form. If you take any linear transformation from V to F, this will satisfy this form, or this is in this form. So this is a theorem. Now we will now write this statement and prove it. So let V be a finite dimensional inner product space. Let V be a finite dimensional inner product space over field F. Okay, V be a finite dimensional inner product space over field F, and let G, this is a mapping from V to F. Let G is a mapping from V to F be a linear transformation, then there exists a unique vector y, then there exists a unique vector, y belongs to V such that g of x is equal to the inner product of x comma y for all x belongs to V. Whatever we see in the last line, we will prove this thing. What is this one? Let V be a finite dimensional inner product space over field F, and G is a mapping from V to F. This is a linear transformation. This is given. Then there exists a unique vector y belongs to V such that g of x equal to inner product of x comma y for all x belongs to V. That means G from V to F is any linear transformation, and for this any linear transformation, this thing will satisfy g of x will satisfy inner product of x comma y for all x belongs to V, and whatever the y we are taking, this is unique. That is, there exists a unique y belongs to V. Now we will prove it. So what is its proof? Since V is a finite dimensional inner product space, so let beta be its basis which contains finite number of elements. So let beta equal to V1, V2 dot dot Vn be an orthonormal basis for V. Be an orthonormal basis. Be an orthonormal basis for V. Since V is finite dimensional, let its dimension be n. So its basis element contains n number of elements. So we are assuming that beta equal to this one, V1, V2 up to Vn, be an orthonormal basis for V. Okay, and let y is equal to, also I am assuming this thing y, let y is equal to summation of I from 1 to n g of Vi conjugate Vi. So this thing I am also assuming. Let y is equal to summation of I from 1 to n g of Vi conjugate Vi. Okay. So after assuming y equal to this thing, now define Now define. Now I am defining another function h. This is from v to f. Define s from v to f by h of vj or h of x is equal to inner product of x comma y. After that, we will make this thing is equal to your function x. Okay. So define s from v to f by h of x is equal to inner product of x comma y, which is already linear. So I am defining this h of x, and since this is an inner product space, so we can say this is a linear, because every inner product space is linear. So since this is an inner product space, so this is linear. So furthermore, for j lies between 1 to n, we have h of vj. H of x is your this one. So what will be your h of vj? This thing we can write. This is your vj comma y. Okay, like this one, in place of x, I have put at this vj. So h of vj is your inner product of vj comma y, and this is your vj comma, in place of I will write y, in place of y I will write this one. So I will write this is summation of I from 1 to n g of vi conjugate vi. Okay. Whatever is this thing associated with this vi, I will take to this outside of this inner product, so this conjugate will vanish, or conjugate of conjugate is again that thing. So if I will take that thing to outside, so what I will write, this is summation of I from 1 to n, this is g of vi. I am taking this portion to outside of this inner product, so this will be vj comma vi. And we know, since all this v1 v2 up to vn are orthonormal basis, so what do we know about this orthonormal basis? Since these things are orthonormal, so v1 into v2 equal to 0, but v1 into v1 is equal to 1. So there is a Kronecker delta, like your del ij or del ji, this thing equal to 1 if I is equal to j, and this thing equal to 0 if I not equal to j. Okay, del I del j means this is just your vi vj inner product of vi vj. So this thing equal to 1 if I is equal to j, and this thing is 0 if I not equal to j. So what will be this one? So for this one I can write this is, first I will write this one, I from 1 to n, this is g of vi into del ji. So if your j will be equal to I, then at that time this will be 1, otherwise it will be 0. So when your I is equal to j, what I will write for that thing, when I is equal to j, at that time this will be 1, and at that time this will be only g of vj will left, g of vj. For other, that means when I is equal to j, at that time this one will exist. So what I can say. So if I will just write one step more, uh, after expansion of this thing, what I will write, this is g of v1 into del summation over I. So g of v1 into del j1. Similarly, g of v2 del j2. Similarly, when for I equal to j, this will be g of vj del jj. And similarly, this thing will continue. The last one will be g of vn del of jn. So when j is equal to j, that means both these things are same. At that time, del ij or this is del jj will be 1, and other del like your del j1, this thing will be 0. Del j2, this will be 0. Similarly, del jn, this thing will be 0. So only thing will be left is g of vj del jj, and del jj will be your 1. So this will be your g of vj. So h of vj is equal to your g of vj for all j from 1 to n. Okay, since, so what we can write, since h and g both agrees or both are agree on beta, so g is also h is equal to g, or so g is h is equal to g. So we can say h equal to g. So whatever I define your h of this thing, h of x equal to inner product of xy, this thing h is equal to g. So you can say your g of x is equal to inner product of x comma y. Okay. So now we will see its uniqueness. What is the theorem? G from V to F. So what we have to show, there exists a unique y belongs to V such that g of x equal to inner product of xy. Now this portion is proved. Now also there exists a unique y belongs to V which satisfies this thing, satisfies this condition. So to show that y is unique, to show that y is unique, so what we will do? Suppose that g of x is equal to inner product of xy dash. That means in place of y, I used another vector y dash. So suppose g of x equal to g of xy dash. So what we defined previously, g of x is your inner product of xy. So inner product of xy will be your inner product of x comma y dash. So from the property of inner product space, we know if these two inner products are same and the first component of the first vector is same, means the second vector will be same. This implies y is equal to y dash by the property of inner product space. Property of inner product space. So now this thing proved. Means there exists a unique y which satisfies g. Okay, so what we prove? So if V is a finite dimensional inner product space over F, and G is a mapping from V to F, or G is a linear transformation from V to F, then there exists a unique Y belongs to V such that G of X is equal to inner product of XY. So in its proof, since V is finite dimensional, we are assuming let V is a basis which contains n element, that means the dimension of V is finite, that means the dimension is n, and this is a basis which contains n elements, and this is the y. What is the unique y? This thing is defined in this way. You have to remember this thing. This is an important thing. Y is equal to summation of I from 1 to n g of vi conjugate into vi, and g of vi conjugate vi, and this is the proof. Now comes to just an example. Define g from R2 to R. Define a mapping or definite linear transformation G from R2 to R by G of x is equal to, defining a linear map, define G from R2 to R by G of A1 comma A2 is equal to 2A1 plus A2. This is a linear transformation. So clearly G is a linear transformation. Clearly C is a linear transformation. You know how to check a linear transformation. Suppose I will say T from V to R is a linear transformation. So how we are checking it? If I will check two properties, this will be T of x plus y equal to T of x plus T of y, where xy belongs to V, where xy belongs to V, and T of alpha x is equal to alpha times T of x, where x belongs to V and this alpha is a scalar. Alpha belongs to F, or you can say this is T from V to F. So if these two property will satisfy, then you will say that T is a linear transformation. Also there is a single property you can check also, T of alpha x plus y. If this thing is equal to alpha times T of x plus T of y, for alpha is any scalar, for alpha is any scalar and x comma y belongs to V, then if it satisfies this property, then we can also say that T is a linear transformation. So clearly you can see this thing is a linear transformation. So how we will see this thing? Since there is a mapping from R2 to R, so G of A1 A2 is like this. So suppose I will take xy belongs to R2. I am taking any element from the domain xy belongs to R2. So suppose x looks like a tuple, since these are from R2, so x will look like a tuple, and similarly let y be b1 comma b2. Then what will be your g of x comma y, sorry, g of x plus y. So g of x plus y means your x equal to this one, y equal to this one. So g of x plus y will be, if we will add this thing coordinate wise, then g of a1, this will be g of a1 plus b1 comma a2 plus b2. So x is this one, y is this one. So if you will add x, you will add x plus y, then this is your a1 plus b1 comma a2 plus b2. So g of x plus y will be this one, and you know g of a1 a2 is this one. So g of this one will be 2 times first coordinate plus second coordinate. So 2 times first coordinate is your a1 plus b1 plus second coordinate is your a2 plus b2. So if we will rearrange this thing, what you will get? This is 2 of a1 plus a2, this one, then 2 of b1 plus b2, and this is nothing. This is just your t of x, g of x, and this is your j of y. Or you can say, or you can write one step more. This is g of a1 comma a2. This is your g of b1 comma b2, and g of a1 a2 is your g of x, and this is your g of y. Okay, and similarly also you can prove that g of alpha x equal to alpha times g of x. Here alpha is any constant or any scalar, and x is here like this one, and also you can show this one. So uh, g is a linear transformation. So what we have to say here, g is a mapping from R2 to R, and g of a1 a2 is defined in this way. Clearly this is a linear transformation. And since here the vector space of the inner product space is R2, so let beta equal to, we have to take an orthonormal basis. Let beta equal to u1 e2, which is your standard basis for R2. So we can let beta equal to u1 comma e2 be the orthonormal basis, for V, or for R2. So if this is your orthonormal basis, then how we are finding our Y? So from the previous theorem, we know how to take your Y. Y is from I is equal to 1 to 2, because there are two elements. You know what is your Y? Y is equal to summation of I from 1 to n G of Vi, G of Vi conjugate Vy. So there are n number of elements in our example, but particularly for this example, this is a two-dimensional. So I varies from 1 to 2, and this is G of Vi conjugate Vi. So what will be G of Vi conjugate Vi means the basis element. So I can write this is I from 1 to 2 G of Ei Q1 E2. At that time we took that V1 V2 like up to Vn. Here we have taken this is only E1 and E2. So this is G of Vi conjugate into Ei I from 1 to 2. So this will be G of E1 conjugate E1, G of E2 conjugate E2. And you know here uh, here G is a mapping from R2 to R. Since R2 to R, so uh, conjugate means nothing because all are real. So you can remove the conjugate. This is G of E1 E1, G of E2 into E2. So what is your G of E1? G of here G of A1 comma A2 is defined as 2A1 plus A2. So what will be G of E1? And this is a two coordinate system. So E1 means this is G of 1 0. So G of 1 0 will be 2 times 1. This will be 2 times 1 plus A2 is 0. So this is only 2. So this will be 2 times, in place of this one you will write 2, and this is E1, 2 times E1. Similarly, what is your G of E2? G of E2 means this is G of 0 1, and G of 0 1 will be is defined in this similar way. So this is 2 times 0 plus 1. This is your 1. So this is 1 times E2. So this is E1 means this is your 1 0, and this is 1 times 0 1. So this is your 2 1. So this is your Y. So Y is your 2 comma 1. Okay. So after getting this Y, then you can verify what is your G of any A1 A2. So G of A1 A2 is, this is the inner product of A1 A2 with 2 comma 1. So what is this one? This is your 2A1 plus A2. Okay. So in this way we are finding our Y which satisfy this thing, or we verified this thing. This is a linear transformation, and we find what is the Y which satisfies that. Here G of X is equal to G of X is the inner product of X comma Y. This is X, this is X, and this is your Y what we found here. So G of X is equal to inner product of X Y, and this is the procedure how to find this Y. So Y is your 2 comma 1. Okay, this in this example it is verified. So now comes to a theorem. Let V be a finite dimensional inner product space. Let V be a finite dimensional inner product space, and T be a linear operator on V, and let T be a linear operator on V, T be a linear operator on V, then there exists a unique function T star, then there exists a unique function T star, then there exists a unique function T star. This is from V to V such that T of x comma y inner product is equal to x comma T star y inner product for all xy belongs to V. For all xy belongs to V. Furthermore, T star is linear. Furthermore, whatever the T star, uh, whatever the T star defined here, and which satisfies this property. Furthermore, this T star is linear. Okay, so whatever the statement of this theorem is saying, let V be a finite dimensional inner product space. T is a linear operator on V. Okay, V is a finite dimensional inner product space. T is a linear operator on V. Then there exists a unique function T star or a unique linear operator T star, such T star from V to V, such that it satisfies this property. That is, what is this property? T of x comma y inner product is equal to x comma T star y inner product for all xy belongs to V, and whatever the T star defined here, that is linear. And you may note that T star, what is defined here, that is the adjoint of T. So note that T star is called the adjoint of T. T star, whatever the T star defined above, is called the adjoint of T. Is called the adjoint of T. So now we will prove this thing. So what is given? V is a finite dimensional inner product space and T is a linear operator on V. So we can note this thing. Given that V be a finite dimensional given that V is a finite dimensional inner product space and T from V to V is a linear operator. This thing is given. Okay. So now start the proof that y belongs to V. Let y belongs to V with any vector or y belongs to V, define G from V to F by G of x is equal to inner product of Tx comma y. So define G from V to F and G of x is equal to inner product of T of x comma y for all x belongs to V. And answer y belongs to V and defining G, which is a function from V to F by G of x is equal to inner product of Tx comma y. T is a linear product, it is given, and here x belongs to V. So what we have to show here, first we have to show here G is linear. First we have to show here, first we have to show that G is linear. So we know already what is the definition of a transform when a transformation is linear. So it will satisfy these two property or it will satisfy this single property. So if we will go to this single property, whatever maybe you can check. So if we go to that single property, so whatever the G is defined here, we have to show that this G is linear. So let x1 comma x2 belongs to V and alpha belongs to F. Then then g of alpha x1, then g of alpha x1 plus x2 will be your g of x is equal to t of x comma y inner product. So in place of x I will add this thing, so this will be t of alpha x1 plus x2 comma y inner product. And you know t from v to v, this is a linear operator. So linear means you can write this thing t of alpha x1 plus x2 as alpha times t of x1 plus t of x2 comma y. So this thing can be written as this is alpha times t of x1 comma y inner product plus t of x2 comma y inner product. So here this alpha can be taken outside of this inner product. So this is alpha times t of x1 comma y plus t of x2 comma y inner product. So this is alpha times t of x comma y, this is your g of x1, and similarly this is your g of x2. So what we got here, g of alpha x1 plus x2 is your alpha times g of x1 plus g of x2, hence g is linear, hence g is linear. So whatever the function or the linear operator we defined from v to f is this one, g of x is your inner product of t of x comma y. We proved that that is linear. Okay, so by applying the above theorem, so here from the above theorem what we know this thing, this is the above theorem. If v is an or v be a finite dimensional inner product space over f and g is a mapping from v to f, or g is a linear operator from v to f, there exists a unique vector y belongs to v such that g of x is equal to inner product of xy. So I will write that thing. So now we define that whatever the g defined like this way, this is a linear. So by the above theorem, we can write by the above theorem, we can say that there exists a unique y belongs to v such that g of x is equal to inner product of x comma y. Sorry, there exists a unique vector y dash, because y is used here, whatever the y is used, this thing are used here. So by the above theorem we can say there exists a unique vector y dash belongs to v such that g of x is equal to x comma y dash inner product. But we have g of x is equal to, g of x is defined in this way, so in place of g of x I can write this is your t of x comma y inner product is equal to x comma y dash. This is your this thing for all x belongs to v. Okay, so there exists a unique vector y dash belongs to v such that g of x is equal to this thing. That means that inner product of tx comma y is equal to x comma y dash. So now defining another linear operator, defining t star from v to v by, since t star is a mapping or t star is a linear operator on v, so define t star from v to v by t of y is equal to y dash. So if I will define t star y in this way, then we can write in the above we have written this is t of x comma y. So we can write t of x comma y inner product is equal to x comma t star y. Okay, this is this one. Just in place of y dash, I have used this thing. This is your t star y, because since t star is a mapping from v to v, so for any y dash here, I will get a y in v. So let it be t star y equal to y dash. So in place of y dash, I will write this is t star y. Now we will show that this t star is linear. Next to show that this t star is linear. So how we will show that this t star is linear? Like this way. How we show that the g is linear? In a similar way, we will show that t star will be linear. So let y1 comma y2 belongs to v and alpha belongs to f. Then for any x belongs to v, we have, and for any x belongs to v, we have x comma t star of this one, x comma t star of alpha y1 plus y2. This thing is equal to, here t star is here. So if I will take t star to first component, so I will write it as t of x comma, then this is alpha y1 plus y2. Then what I will write, this is t of x with alpha y1 plus t of x with y2. Then here alpha can be taken outside of this inner product space. So we will write this is alpha bar, this is t of x comma y1, and this is t of x comma y2, and then alpha bar is here. Then t of x comma y1 can be written as x comma t star of y1, x comma t star of y1, and this is x comma t star of y2. Then this alpha can go to inside of this inner product space, so we will write this is x of alpha bar, sorry, here alpha bar, if it will go to this place, then this will be alpha, so this will be alpha t star y1 inner product, then this is inner product of x comma t star of y2. Then this will be x comma, so if you will add this thing, this will be x comma alpha times t star y1 plus t star y2. So what we got, inner product of x comma t star of alpha y1 plus alpha y2 is equal to inner product of x comma alpha times t star y1 plus t star y2. So this is your inner product of x comma t star of alpha y1 plus y2 is equal to this one, and these two inner product are same. If the first component is same, then second component it would also be same by the property of inner product space. So you can say t star of alpha y1 plus y2 is equal to this second component. This is alpha times t star of y1 plus t star of y2. So here we show that t star is linear. This thing equal to this thing, then you can write, since x is arbitrary, then t star of this one equal to this one, thus t star is linear. So finally we have to show that t star is unique. Finally we have to show that t star is unique. So whatever the T star what is the urgent linear operator of T, that is linear, we have proved, and next we have to show that this T star is unique. So suppose S is a mapping from V to V is linear. That means I am taking which will satisfy this property of T star. So S is a mapping from V to V is linear and it satisfies the properties of T star. So what is the properties of T star? We took that is T of x comma y. This is equal to x comma T star y. We already took. So I will write this thing. Uh, since we have to show that T star is unique, so in place of T star, I am saying that suppose there is another linear transformation S from V to V which is linear and also it is satisfying this property x Tx comma y inner product is equal to x comma S of y. Suppose this thing is satisfying this one, but we know Tx comma y inner product, this thing is equal to x comma T star y. So this is your x comma S of y. Here also the same thing. Two inner products are same and the first component is same. This implies you can say your T star y is equal to your S of y. So if you will take uh, or if you can say there exists another transformation from V to V which is linear and it satisfies this thing. This is nothing. This is just same as your T star. So T star is unique. So T star is S, and whatever the T star described above, T star is whatever the T star described above, this is equal to a urgent of T. The, the T star described above is nothing but the urgent of T. Okay. So just say again the statement. Given that V is a finite dimensional inner product space, T is a linear operator on V. So this thing are up to this thing are given. You have to show there existed unique function T star from V to V such that Tx comma y inner product is equal to x comma T star y for all x y belongs to V. And furthermore, T star is linear. So whatever the T star is defining in this way, here we have to prove that this T star is linear and this T star is unique. So to get this thing, we have defined there g is any function from V to f which satisfies g of x is equal to inner product of tx comma y. Okay, and here we show that this is linear. Then after seeing this thing, uh, I have defined another linear transformation T from V to V such that T star y equal to y dash which satisfies this thing. Okay, in this way I will prove it. Here T star is linear, we already proved, and this T star which satisfying this property, this is unique. Okay, you just see it. Then come to another thing. So if T star is a adjoint of T, if T star is a adjoint of T, if and only, or T star is a adjoint of T, if and only if inner product of Tx comma y equal to x comma T star of y. That means if T changes its position from first to second, then there is a star or as a conjugate transpose. Similarly, if we will consider x comma t of y, so if we consider x comma t of y, then this thing can be written as t of y comma x, t of y comma x by taking its conjugate. Okay, x comma ty equal to t of y comma x conjugate. So now t of y comma x can be written as, this is y comma t star of x, and y comma t star of x can be written as, if I will remove the conjugate, then this thing will be written as t of x comma y. Okay, so what we got here, x comma t of y inner product is equal to t star x comma y inner product. That means if the place of t changes from first to second or second to first, you will give a star here. Okay, so you may note another thing. Let V be a finite dimensional inner product space. Let V be a finite dimensional inner product space, and let beta be an orthonormal basis for V. Beta be an orthonormal basis, an orthonormal basis for V. V is a finite dimensional inner product space, and beta be its orthonormal basis. So if T is a linear operator on V, if T is a linear operator, if T is a linear operator on V, then what will be the corresponding matrix of T star with respect to this basis beta? This is nothing, this is just the conjugate transpose of this matrix which is associated with this transformation T with respect to this basis beta. That means T star of beta is equal to T beta star. And what does the meaning of this one? T beta, that is the matrix associated with, the transformation T, associated with the transformation of this operator T with respect to this basis, or with respect to this orthonormal basis beta. Whatever the beta we are using here, that is the orthonormal basis for V. With respect to this orthonormal basis, beta. Okay. Now I'll just see a problem. Example, let T be a linear operator on C2. Let T be a linear operator. Let T be a linear operator on C2 defined by T of A1 comma A2 is equal to 2iA1 plus 3A2 comma A1 minus A2. So this is a linear operator on C2 defined in this way. So since the vector space is C2, so what is the standard basis for C2? So we can write the standard basis or the standard basis or so the orthonormal basis. Whatever you can say that will be okay. So the standard basis. So the standard basis or the orthonormal basis for C2 is your E1, E2, that is your beta equal to E1, E2, or whatever you are writing, this is 1, 0, 0, 1. So whatever will be your T beta now, so if the transformation is your this one, so whatever is your T beta, that is the matrix T beta means the matrix associated with this transformation T with respect to this orthonormal basis beta. So whatever your T beta now, okay, so now our aim is to find what is your T beta. Okay, whatever is your T beta, we have to find this thing. Your T of A1, A2 is this one. So whatever your T of E1, this is your T of 1, 0. So in place of A1 you will put 1, in place of A2 you will put 0. So T of 1, 0 will be 2I comma 1. Similarly T of, so 2I comma 1, this thing, you know, this thing can be written as 2I times E1, 1 times E2. Similarly T of E2 can be written as, this is T of 0, 1, which is your, in place of A1 you will put 0, in place of A2 you will put 1. So this thing will be 3 and minus 1. So this is your 3 times E1 minus 1 times E2. So whatever will be your T beta, you will write the coefficient of E1 and coefficient of E2 in column vector. So this will be 2I1, 2I1. Okay, and similarly in the second column you have to write the coefficient of E1 and E2. This will be your 3 comma minus 1. So this is your T beta. So if this is your T beta, now our aim is to find what is your T star of beta. That means my question is to find what is the matrix associated with this adjoint operator T star with respect to orthonormal basis beta. So our T star beta is nothing. This is just the star of T beta. And star of T beta means this is the star means this is the conjugate transpose of T beta. So T beta is your this one. So what is its conjugate transpose? So conjugate transpose. So how you will write the conjugate transpose? So first I will take the conjugate. So what is the conjugate of T beta? This is minus 2y and this is 3, this is 1 minus 1. Now what is its transpose? This is minus 2y3, this is 1 minus 1. So this is the conjugate transpose. So this is your T star beta, that is the matrix associated. This is the matrix associated with this adjoint operator T star with respect to basis beta. So this is the matrix. So like this is the T of A1, A2. So what will be a T star of A1, A2? This is the matrix associated with this T star. So what will be the T star of A1, A2? If A1, A2 is any element of C2 or any vector of C2, so what will be its T star? So if this matrix transformation is given, so you just uh, multiply with this matrix with this column vector. That means you have to write this is minus 2y1 3 minus 1 into this column vector a1 a2, then first row first column, then this will be minus 2i a1 plus a2 comma 3a1 minus a2, 3a1 minus a2. So this is your answer. So if a transformation is given to you, and since the vector space is given to you, you can find its standard basis or find its orthonormal basis. So after finding the orthonormal basis, you can find this the t beta or the matrix associated with this transformation T. Then you will find what is the matrix associated with this adjoint operator T star. So after getting this one, then this is the T star of A1 A2. So if T is given to you, then how you are able to find its adjoint operator. So this is the example, or this is a perfect example how to find the linear operator of T if T is given to you. Okay, today is only this much. Thank you.